This is the lecture for remembering. If you haven't already done so, please open up the PowerPoint entitled Remembering. The study of memory is a huge research area in psychology. We can study memory from a developmental standpoint, that is, how good is our memory at different ages. We can study it from a cognitive standpoint, that is, when two people engage in a conversation, what do those two people walk away from that conversation remembering? Oftentimes, our memory is not perfect. People who tend to have good memories do tend to be good at coding memories in different ways, but not all of us have a great memory. So in this lecture, I'd like to talk a little bit about the different types of memory, how our information tends to be stored, tips for improving memory, what happens when we lose information, and then one of the most well-known diseases of memory, which is Alzheimer's disease. So to begin today, I'd like to do a little activity. I'm going to slowly read you a list of words, and I just want you to keep those words in your head. Then I'm going to say 3 words, and I want you to be able to tell me whether or not those words were on the list. So here is the list. Please listen carefully. Rest, tired, awake, dream, snore, bed, eat, slumber, sound, comfort, wake, night. Now I'd like for you to just answer to yourself if the following word was on that list. Was the word couch on that list? Second, was the word sleep on that list? Third, was the word tired on that list? Most people correctly identified that the word couch was not on that list. Most people also correctly identified that the word tired was on the list. But what is most interesting as a memory phenomenon is that most people mistakenly say that the word sleep was on that list. If you go back to listen to that list again, sleep was not one of the words that I had mentioned. However, because most of the words in that list were around the theme of sleep, we erroneously assumed that the word sleep itself was part of that list. So that's just one example of the imperfection of our memory. Memory tends to be good in most of us, not great, and certainly not perfect. There is a very, very small percentage of people who have what we call photographic memory. In psychological terms, it's called eidetic memory. However, this kind of memory isn't exactly what you would always want. People who have this kind of memory tend to memorize things in terms of pictures or images. So every time I see you, it's almost like I'm seeing a new person because I have a perfect mental representation of you from the last time I saw you. So it actually becomes pretty difficult for some of these people to engage in their day-to-day lives. They have a jumble of images in their heads that they find difficult to keep straight, and it's almost as if they're relearning people and re-recognizing faces every time they encounter the same people over and over again. So photographic or eidetic memory might not necessarily be something that you wish for, although it's totally understandable that before exam time it might be something that you wish you had. If you take a look at the first slide of this PowerPoint, you're going to see the title of Multi-Store Model of Memory. This is the model of memory that psychologists have really based our study of memory on since the late 1960s. Although this model has been embellished and there have been other components added to it, we really do not have a better alternative for how we believe memory is structured. This model assumes that at some level, different types of memory are stored in different areas of the brain. So that's why it's called the multi-store model of memory. We have 3 different types of memory. As you can see from the slide, we have sensory memory, short-term memory, and long-term memory. Presumably, they are stored in different areas of the brain, but of course there is some disagreement as to where information is actually stored. We no longer believe that there is one repository for short-term memory and there is one repository for long-term memory, for example, but we do know the structures that are involved in those types of memory because we know that when we do damage to those structures, or if those structures are damaged by accident or stroke or disease, those types of memory are impaired. If you take a look at this model, you'll see that we have 3 memory stores and that there are cognitive processes between each one. Sensory memory is our shortest memory span. I'm going to talk more about it in a second, but this is a very brief store, just to hang on to information that comes in from all 5 senses. Most of the time, if it is information that we pay attention to and actively rehearse, it will go into short-term memory, where it's held for a small period of time. Then with more active rehearsal, it will move into long-term memory. So this approach assumes that memory is a very active and intentional process, but as you know, that's really not the case. We know all kinds of stuff that we never tried to learn or remember intentionally. So there is some information that does move from sensory to short-term to long-term without any active cognitive effort on our part. It tends to happen with information that we are bombarded with constantly, and it just ends up sticking in our long-term memory, even though we had no intention of remembering it. But for the most part, we assume that memory is an active process. Now, if you look at the double arrow moving from long-term memory back to short-term memory, you will see there's another process called retrieval. Retrieval is how we bring information from long-term memory back into our short-term or active memory. This is not a perfect process, and again, sometimes we may have thought that we've forgotten something when really the problem is a retrieval problem. The information is there, but we have somehow lost the link or lost access to it in long-term memory. But then suddenly 2 weeks later, it pops into our head without any warning at all. So there are still a lot of mysteries to memory, but this is our basic idea of how memory works for us. If you go to the next slide, there's a little bit more information about the 2 types of memory that I want to talk about first: sensory memory and short-term or working memory. Sensory memory is our shortest memory store. At most, it only lasts for a few seconds, so the duration is very short, but the capacity, in theory, is infinite. We are constantly bombarded with information from all 5 of our senses. So in theory, sensory memory can hold millions of pieces of information, but most of it gets filtered out just as soon as it came in. For instance, imagine you're driving down a busy road. You may see hundreds of cars pass you by, but a few moments later, you might be hard-pressed to identify even one car that passed by unless it was novel or personally relevant to you for some reason. So that's the job of sensory memory, to take in many pieces of information, but to very quickly filter out most of the information that is totally irrelevant to us. Although sensory memory does come from all 5 senses, hearing, vision, taste, smell, and touch, I really want you to only know the 2 major types that we pay attention to: iconic and echoic. Iconic sensory memory is visual sensory memory. The most basic unit of visual input is called the icon. So visual sensory memory is known as iconic memory. This store only lasts between a half second and maybe 1.5 seconds. A very simple example of this is if you are looking at someone with a sparkler or a glow stick spinning it around at night. You will notice that there's kind of a brief trail of light, and then just as soon as it was there, it's gone. That's an iconic memory trace. The visual memory is briefly there, and then just as quickly, it's gone. So we take in visual memories very, very rapidly. But like I said before, most of that just gets wiped from the slate almost as quickly as we saw it. Echoic sensory memory is memory for sounds. The basic unit of sound is known as the echo. Echoic sensory memory lasts a little bit longer, on the order of 4 to 5 seconds. The reason for that is very useful. If I say a sentence, it might take me 4 or 5 seconds to get from the beginning of the sentence to the end of the sentence. If your echoic memory was shorter than that, you wouldn't be able to process what I was saying because you would have already lost memory for information at the beginning of the sentence, so you couldn't put it together from information at the end of the sentence. So there's a very good reason why echoic memory lasts just a little bit longer, because sometimes auditory information must be kept in that little loop a little bit longer to put the entire meaning together, to understand and make sense of the input that was coming in. So again, sensory memory has an extremely short duration, but in theory, an infinite capacity. The next store is short-term or working memory. Psychologists believe that this is the most active form of memory that we have, because short-term memory is simultaneously processing information that comes in from sensory memory and also actively in the retrieval process of information coming from long-term memory and trying to make sense of all of it and trying to distribute it to where that information needs to go. So psychologists began calling this working memory to reflect that this is our real active memory store. Short-term memory is limited in both capacity and duration. The capacity for short-term memory is between 5 and 9 items. 5 and 9 items. There is a, quote, magic number in psychology for the capacity of short-term memory. We talk about the capacity of short-term memory as being 7 plus or minus 2 items. 7 plus or minus 2. So that's where we get 5 to 9 items. The duration of short-term memory is about 20 seconds. In the old days, it might be just long enough for you to open the phone book, look up the number for your favorite pizza place, and repeat it over and over to yourself until you can get to the phone to dial the number. By the time you dial the number, it's forgotten. You've only held that information for about 20 seconds. So in the absence of any active, intentional rehearsing, information is only stored for about 20 seconds. I want to go back for a second and talk about the capacity of short-term memory. As I said before, the capacity is very limited, 7 plus or minus 2 items. When you begin to think about that, it may not be a coincidence that some of our most important personal information is within that range. Think about a phone number. Back in long time ago, most people that you knew, family and friends, lived within the same area code, so it really wasn't necessary to memorize an area code. You did, however, have to memorize phone numbers. Phone numbers are 7 digits long. Zip codes are 5 digits long. Even with the +4 designation, we're still within 9 numbers. And another important personal number, our Social Security number, is still within 5 to 9. It's still within that magic number. I'm not sure if it's a coincidence or not, but I would say that if those numbers were much longer, we would have a more difficult time remembering them. Because our capacity for short-term memory is limited, we can engage in a process called chunking. Chunking is where we can take several apparently disjointed items and put them together in meaningful chunks so that the overall number of items is smaller. For an example, go ahead and take a look at the next slide. The next slide has examples of a series of letters. And if you look at the first series of letters, if I'm looking at this series, I would probably have to remember them separately, but already my mind is trying to put them in chunks. Instead of trying to remember G, E, X, M, U, N, F, O, L, B, E, P, etc., my mind is already saying Gex, Mun, Fa, Bep, Raj, Tev, Kig, trying to put those separate letters into chunks so that I would end up with a manageable number of pieces of information instead of this string of individual letters. If you take a look at the second example, the chunking process gets a little bit more easy, and if you look at the third string, you can see why. The second series of letters are already in meaningful chunks. FBI, CBS, DVD, CIA, etc. are already meaningful to us. So those letters chunk almost automatically. So again, instead of having to remember this string of unrelated, separate letters, we only have to remember approximately 7 chunks of information, and that is within the realm of short-term memory. So chunking is a process by which we group information into meaningful chunks to extend our short-term memory capacity. If you go back for a second to the previous slide, under short-term memory, you're also going to see information about the phenomenon of the serial position effect. When we are asked to memorize information in a list, we are more likely to remember the first items on that list and the last items on that list. This is because short-term memory is limited in capacity. There's only so much I can keep in there at one time, so if you give me a long list of things to remember, unfortunately, the middle stuff starts to fall out. So again, the primacy effect is our tendency to remember items at the beginning of the list, in other words, at the beginning serial position. The recency effect is our tendency to remember items at the end of the list, or at the end of the serial position. This does actually have important applications. For instance, if you're studying and you sit down and study for an hour, you are much more likely to be able to remember the information you studied at the beginning of that hour and at the end of that hour than what was in the middle. Professors are aware of this too, well, at least the good professors. Students are much more likely to remember information at the beginning and the end of a lecture than the information in the middle. So if a professor was smart, he or she would organize a lecture such that the most critical information came at the start or finish of class, because attention starts to drift in the middle, and at the same time, information is lost in the middle of a lecture. So that's what we mean by serial position effect. Information at the beginning and the end of a list or a series are better remembered than information in the middle. Next, I'd like for you to skip to the slide after chunking that has multi-store model. On this slide, you're going to see the last memory store, which is long-term memory. Long-term memory is probably what most people think of when they think of memory. It is where information is more or less permanently stored. Long-term memory, in theory, is of infinite capacity and infinite duration. Infinite. So for example, if I could somehow get the correct link into your long-term memory, you would be able to tell me what you had for lunch on this day 5 years ago. The information is there. Presumably, the information is there. Whether or not you believe that is another issue entirely. Now, of course, you can argue, well, I really didn't actively rehearse what I was eating that day, so maybe that information never got to long-term memory. That is true. Of course, that is true. But if the information is there to be retrieved, according to this model, it is still there. If you can't remember it, it's a problem with retrieval, not a problem with laying down or storing the information in the first place. When we talk about the processes involved with long-term memory, we usually talk about 3. The process of consolidation is the process of moving information from short-term to long-term memory. Most psychologists theorize that this process takes a few hours. So in other words, if you study something, that information needs a couple of hours to move from short-term to long-term memory. If you sit in a lecture, that information takes a couple of hours to move from short-term to long-term memory. So people who are studying for a test usually don't benefit by studying 10 minutes before a test, because that information really isn't getting permanently laid down in long-term memory, presuming it never got laid down in the first place during class. So consolidation is moving from short-term to long-term memory. Storage is the actual process of storing long-term memories. And I'm going to talk in just a little bit about the structures that we believe are involved in storage. But again, our view of memory as it currently stands is that there is just not one final resting place for memory. Memory is much more complex. It is more likely that memories are stored in a network of neurons between structures. But there are, like I said, a few structures that are implicitly involved in memory. The last process is retrieval. Retrieval is retrieving information from long-term memory back into short-term memory so it can be used. When we think of retrieval, we usually think of 2 kinds of memory: recall and recognition. Recall and recognition retrieval. Recall is when I simply ask you to recall a piece of information. So for example, which brain structure is involved in maintaining respiration and heart rate? That's a retrieval question. You have to bring that information back from long-term memory. Hopefully you remember that that structure is the medulla. The other type of retrieval is recognition, and in recognition memory, I present to you a series of options and you have to recognize which one is the correct one. So if I was to say, which brain structure is responsible for maintaining respiration and heart rate, is it the cerebellum, the frontal lobe, the hypothalamus, or the medulla? You would be able to recognize that it is the medulla. So recognition memory I want you to think of as more or less a multiple choice test. Recall would be more an open-ended question where you just have to simply recall that information. Now we do have several types of long-term memory. The 2 major divisions of long-term memory are known as declarative, which is also known as explicit, or procedural, which is also known as implicit. Declarative memory is memory that you can declare. It is facts. It is knowledge. You know, who was the first president of the United States? Where did you go to elementary school? Who was your 8th grade math teacher, for instance? Information that you can declare are known as explicit or declarative memories. Information that you cannot necessarily declare that is, it would be much harder for you just to simply write down, is known as procedural or implicit memory. An example of procedural memory is remembering how to ride a bike, remembering how to play piano, remembering how to drive a manual transmission if you've ever had to drive a stick shift. It would be really hard to write those things down step by step and have someone be able to follow them. It's possible, but that is not the best way to transfer that kind of memory. So memory for skills or memory for procedures is usually referred to as procedural or implicit memory. Both kinds are very important. And what we have found over the years in research with people who have lost portions of their long-term memory is that it is very likely for a person to lose declarative memory. That is, they lose memory for facts and knowledge, but at the same time retain procedural memory. So a person might forget all the facts that he or she learned in school, but still remember something like how to play the piano. So that really led us to believe that there are two very different types of long-term memory that serve different purposes. Declarative memory has a further subdivision, and we call this the semantic episodic distinction. Semantic and episodic memory are both forms of declarative memory. In other words, they are memory for facts or knowledge that we can declare. But there is a difference in the type of information we're talking about. Semantic declarative memory is what I would call shared knowledge or shared facts. We can all say, for instance, what date did the World Trade Center towers fall? We can all say, for instance, what day is Valentine's Day? That is shared declarative memory. We all have common knowledge of those facts. Those are examples of semantic memories. However, each of us also has a personal autobiographical memory that we could declare. We may not, but we could declare. That is called episodic. So for instance, although all of us are very aware of the date of the World Trade Center attack, all of us have a unique memory as to what we felt, where we were, those kinds of pieces of information. Those pieces of information are known as episodic. So episodic is still declarative in that we still could declare it, but it is a personal autobiographical record that is not shared with anybody else. Another example, again, we may all agree and know that Valentine's Day is February 14th, but we all may have a personal episodic memory of what we did that day, how we felt that day, the types of interactions we had with our significant other on that day. Those would be episodic declarative memories. So that's the distinction. Both declarative, but semantic is shared, episodic is personal. If you take a look at the next slide, I want to show you some of the brain structures that are involved in memory. And some of these you learned about when we talked about the brain and behavior. So I just want to remind you of some of those structures. Long-term memory we associate with two structures in the brain, the amygdala and the hippocampus. We believe the hippocampus is critical for the storage process of long-term memory. In other words, it is critical for laying down long-term memories, but we do not believe that this is where long-term memories are ultimately stored or housed. We think of the hippocampus more as the switchboard that directs the neuron networks that actually store the memories. We do know, however, that damage to the hippocampus can and usually does result in memory loss. It's as if the switchboard operator is no longer functioning, so we don't have links to those long-term memories anymore. So when we say long-term memory, usually the structure that is associated with it in terms of storage is the hippocampus. The other structure involved is the amygdala. Remember, the amygdala essentially sits next to the hippocampus, and this is the structure that is involved with coding the emotional content of memories. So if you have a memory that does have significant emotional content as well, the amygdala gives it that extra stamp. So you have storage for the emotional content of a memory as well as the actual event itself. This is why we believe that emotional memories tend to be better remembered than just everyday run-of-the-mill memories. That is not to say that our memory for emotional events is perfect, however, because sometimes neurotransmitters and hormones that are released during emotional or even traumatic events can impair our attention processes as we are experiencing the event. So our memory might be more powerful, but it may not necessarily be more accurate. So that is something important to keep in mind. We may have a strong memory of an emotional event, but that does not necessarily mean that it is better or more accurate than our memory for an everyday run-of-the-mill event. For short-term memory, the area of the brain that is most associated with this function is the prefrontal cortex. That is the part of the frontal lobe that is the furthest forward. In other words, the part of the frontal lobe that is right behind our forehead. That's the prefrontal cortex. We know from clinical examples that people with prefrontal cortex damage have problems with short-term memory. It's not to say they don't have any, but their short-term memory capacity and duration are often negatively impacted with that kind of damage. So again, we talk about the prefrontal cortex as being important for planning and strategizing and all of those higher order cognitive functions. Well, a lot of times that requires information from long-term memory. So if that area is damaged, those functions are also impaired. Sensory memory is a little bit less clear. We believe that that takes place in different brain areas. Again, because the duration is so short, it is hard to pinpoint exactly where that memory is laid down for those brief few seconds. Short-term and long-term memory are a little bit better understood. If you take a look at the next slide, I do want to mention that while we have this multi-store model of memory that includes sensory memory, short-term memory, and long-term memory, there is also a complementary approach to understanding how memory works. So I want you to think of the multi-store model of memory as kind of a what. What is stored, maybe, and where it is stored. Levels of processing is more about how information is stored. The way in which we process information leads to either better or worse memory for it. So this model is complementary to the what and where model. I want you to think about this as a how model. When we are presented with information that we are expected to remember, we can engage in one of two processes: shallow processing and deep processing. Shallow processing uses the process of maintenance rehearsal. This is when we simply repeat information to ourselves over and over again, simply to maintain it, with the hopes that sheer repetition is somehow going to get that information from short-term to long-term memory. Or you may engage in some other kind of shallow processing. What does this word sound like? What letter does this word start with? But you're really not linking it to anything significant. So people who engage in just sheer repetition to try to remember something are much less likely to actually remember the information from the time comes. So as a study strategy, for instance, shallow processing is not likely to work. If we have a student who just sits and flips through his or her notes over and over again and says, well, if I look at this information enough times, it's going to sink in, it's probably not going to sink in. That is an example of maintenance rehearsal. Simply looking at the information over and over again and doing nothing more with it. That is less likely to produce good memory for that information. What is more likely to produce good memory for information is what is called deep processing, the deep level. And this requires elaborative rehearsal. In general, elaborative rehearsal is when we take that information to the next level. We elaborate on it. We associate it with something that we know, something that has meaning to us. The information is processed in a much deeper way. So instead of simply repeating information over and over again, we try to tie it to something that we know. We try to assign it personal meaning to us. We try to make the information relevant to us. The more links we can establish to that new information, the more likely it is we're going to be able to remember it. A couple of examples that you see on that slide of elaborative rehearsal are the generation effect and the self-reference effect. In the generation effect, we are more likely to better remember information if we generate it. So for instance, if I have to get a list of several things from the grocery store, I am much likely to remember it if I had to first sit down and write out the list than if someone just handed me a list and said, here, remember these things and then go to the store and get them. The reason is, when I had to sit down and write that list, I was probably thinking about what those foods would be used for. Oh, this is going to be for lunch this week. I need this to make a dinner. I need this to make cupcakes for somebody's party. In other words, each item on that list is associated with something else. It is an item that is associated with some kind of meaning. So if I go into the store having memorized that list, I'll be much more likely to get everything I need. If someone just hands me a list and says, here, see these 10 things, memorize it, go in that store and get it, these items aren't attached to anything in my head, so it's much more likely that I'll be able to clearly remember everything, especially if that list starts to exceed our short-term memory capacity. The second effect is called the self-reference effect. And this happens when you can take information that you need to remember and somehow make it referential to yourself. For instance, it is very easy for me to memorize my mother-in-law's birthday because it's the same date as my parents' anniversary. Her information, which was at one time new to me, is self-referent. I already have some information that I can tie that to, so I'll never forget that piece of information. So when you can tie something to something personal to you, it makes you much more likely to remember it. That is the self-reference effect, taking information and making it personally relevant to you. If you take a look at the next slide, I want to talk a little bit about information loss. Kind of forgetting, but I don't want to use the term forgetting. In psychology, we tend to use the word information loss because this designates that we can lose information at several levels. We can lose information in short-term memory or in long-term memory. Usually when we use the term forgetting, we're really referring to not being able to retrieve something from long-term memory. And of course, that is definitely one type of information loss, but it is certainly not the only type of information loss. The first type of information loss that I want you to know is when we try to bring information from long-term back into short-term memory. We have what's called interference. Interference is basically when you have two competing pieces of information, One wins out, one doesn't win out. That's interference. And in memory we have two kinds, proactive and retroactive. Proactive interference is when old information interferes with new information. Old information interferes with new information. I hate to use shallow processing here, but I'm going to. I think of the letter O in proactive and think old. Proactive, old interferes with new. Again, that's shallow processing. I hate to use cheap gimmicks, but it works for me. The O in proactive reminds me that the first word is old. Old interferes with new. So to give you an example, think about old interfering with new. So that is, I have to use a new password for my computer at work, and I keep typing in my old one. That is proactive interference. Old interferes with new. The other type of interference is called retroactive interference. New information interferes with old information. New information interferes with old information. An example of this might be a phone number. If you get a new cell phone number, very quickly you can't remember your old cell phone number. Not that it matters, but new information interferes with old. It's almost like it overwrites it. That's retroactive interference. So I want you to stop for a second. I'm going to give you an example, a very egregious example, and I want you to be able to identify whether this is an example of proactive or retroactive interference. Here's the example. Calling your new significant other by your old significant other's name. Ooh, it makes me feel bad just thinking about it. Let me say it again. When you call your new significant other by your old significant other's name, can you identify which kind of interference this would be? This would be an example of proactive interference. Old interferes with new. So if it ever happens to you, say, honey, I'm sorry. It's just proactive interference. And see if that gets you off the hook. It might. Give it a shot. That is a horrible example, an embarrassing example, but it is an example of our memory problems at work. That is proactive interference. Another type of information loss that is pretty commonly known is called amnesia. Amnesia is just simply information loss, loss of memory. There are many different types in psychology. They are diagnosed for a multitude of reasons, but amnesia is simply information or memory loss. If you take a look at the next slide, I want to go over the two types of amnesia. A person can have both. The first one is called retrograde amnesia. The second one is called anterograde amnesia. The way that we define what type of amnesia a person has is by first identifying some event. So where you see onset of amnesia, that is the event that serves as our marker. That event can be physical injury, traumatic brain injury, a car accident, something like that, a blow to the head. That can be the actual event, the onset. Sometimes it's a little bit more gradual. So if you have a progressive brain disease or a brain tumor that develops over time, it may be a little bit more difficult to actually identify that one moment in time so that we can differentiate between retrograde and anterograde amnesia, but it's usually still possible. But I want you to remember that that onset may not be necessarily of only a physical cause. Psychological trauma can also serve as our event. For instance, witnessing a horrific crime can be a psychological event even though no physical damage was done to the person's brain. But that can still produce amnesia. So I want you to remember that amnesia can be the result of either a significant physical or psychological trauma. It doesn't matter. The net result or effect on memory can be essentially the same: amnesia. Retrograde amnesia is amnesia or memory loss for information before the event happened. Anterograde amnesia is memory loss after the event. So again, I hate to resort to shallow processing, but the way that I keep these straight is to say anterograde after. They both start with the letter A. Anterograde amnesia is memory loss after the event. Retrograde amnesia is memory loss before the event. The most debilitating situation is when a person has both anterograde and retrograde amnesia, which is possible. So I want you to think this through. If there is a significant event that happened and a person cannot remember the hour leading up to that event, what happened in that hour leading up to the event, that would be retrograde amnesia. If the person cannot remember what happened all the way through an hour after the event, that is anterograde amnesia. When we do see incidences of brain trauma, for instance, if someone was in a car accident, we can see both. We can see memory loss for events just leading up to the accident and maybe a few moments after the accident. So that's not uncommon to see both retrograde and anterograde amnesia. But to see it long term, for years leading up to the event and years after the event, that's a little bit less common, but of course still possible. So that's the difference. We have to use some time marker, some event marker, to differentiate between retrograde and anterograde amnesia. Anterograde amnesia really ends up being the inability to lay down new memories, whether that's for just a few moments, hours, days, weeks, months, or years. That's how we see it manifest. It's the ability to lay down new memories. If you go back to the slide on information loss, you're going to see the heading of false retrieval. And this is something that I've mentioned over the course of this lecture. Our memory is not perfect, and sometimes we actually remember information erroneously. There has been a lot of research done on this because it is so crucial for something like a court case where you have eyewitnesses recounting an event. We have to make sure that that person's account of the event is accurate, that they aren't remembering false details or information was not somehow implanted into that person's memory. The picture of the person that you see on this slide is a woman by the name of Elizabeth Loftus. Loftus is a psychological researcher who has done most work to date on false memory. She has studied the effect of wording of questions on people's memory. She has studied the extent to which we can implant a false memory into people. And of course, in an experimental setting, it's fairly benign. With repeated suggestion, for instance, I may be able to suggest to you, as Loftus did in her studies, that when you were very young, you got lost in a mall and you couldn't find your parents, and some elderly lady sat with you and bought you ice cream until your parents came back to get you. Now, although that hasn't happened to most of us, if it is stated in such a way that we were very young and the details seem realistic, we may come to believe that that actually happened because we have no reason to believe otherwise. We have no information to the contrary. So there is definitely a potential for false memories. because our memory is not perfect and is heavily influenced by suggestibility. With respect to the influence of wording, Loftus did a series of very interesting studies in which she would have groups of people watch a film clip and then later ask questions about the film clip, and the way in which the questions were worded influenced the response that the people gave regarding their memory. In the classic study, she had people watch a film clip, a pretty boring film clip of a car roll through a stop sign and rear end another car. The end. Not too much to it. Everybody saw the same video. For one group of people, she asked about how fast was the car going when it collided with the other car. And they would say, I don't know, maybe 5-10 miles an hour. For the second group of people, Loftus asked about how fast was the car going when it hit the other car. And the average estimate was a little bit higher. Oh, I don't know, 10, maybe 15, even 20 miles an hour. And for the third group, she asked about how fast was the car going when it smashed into the other car. Oh, 15, 20, maybe 25 miles an hour. Notice the wording of the question influenced the participants' quote memory of that event. The eyewitness memory changed simply based on how the question was worded. So hopefully you can begin to understand and appreciate the ramifications that that would have in a court when you're questioning an eyewitness. The wording of the question suggested a speed. When you use the word collided with, it doesn't make it sound very fast at all. Hit makes it sound like it should have been a little bit faster. Smashed into suggests that that car was really moving when it hit the other car. In other words, we might tailor or change our memory to be a little bit more consistent with the wording because the wording suggests something very specific. Now for those same subjects, a week, maybe a few weeks later, she asked them, in the video, was there broken glass? The people who had the original question of collided with were much more likely to say no, there was no broken glass in the film. The people who had been asked how fast was car going when it smashed into the other car were much more likely to say yes, there was broken glass. In the video clip, there was never any broken glass. But because it is more consistent to believe that a high-speed crash would be associated with broken glass, of course our memory becomes a little bit more malleable. It is more consistent to say, well, if I thought that car hit that other car at about 25, 30 miles an hour, there probably should be broken glass, therefore there was. So although there was no broken glass in the video, people who had that third type of question were much more likely to say that there was. So again, it just reiterates this idea that our memory is not perfect. It is very malleable, and whether good or bad, it is often subject to the power of suggestion. Just something to keep in mind. If you advance past the amnesia slide, I want you to take a look at the next slide about Alzheimer's disease. I did want to mention Alzheimer's disease because it is the most common and one of the most well-known diseases of memory. Alzheimer's disease is characterized by progressive memory loss. It is usually associated with aging, but it is not caused by aging. That's very important to remember. Getting old does not mean getting Alzheimer's disease. It just becomes more common as you age. In fact, among the population of 85-year-olds, almost 50% of the population has Alzheimer's disease. Alzheimer's disease usually has an onset in the 50s and 60s. In some cases, it can be even earlier. But because there is so much public knowledge and awareness of Alzheimer's disease, people are much more likely to recognize it now than they might have been 20 or 30 years ago. Alzheimer's disease can start with just simple memory lapses. Where did I put my keys? Oh, I forgot I was supposed to have lunch with this person today. But then the memory lapses become more common. They become more frequent. As Alzheimer's disease progresses, people may begin to forget names of people very close to them, names of loved ones, names of close friends. They may forget their address. They may forget, where they purchased something or why they purchased something. So we begin to see more significant lapses in memory. As Alzheimer's disease progresses further, we begin to see a need for care. As the memory lapses progress, that is associated with progressive brain disease. And eventually, we begin to see the disease progress to areas that are responsible for things like swallowing, using the bathroom, and just basic care and grooming. So at some point, for most people with Alzheimer's, assistance is needed, because a person with Alzheimer's disease might get to the point where he or she forgets how to dress him or herself. Forgets that when it's warm outside, you don't need to put on 4 coats. That lapse in memory and judgment requires some sort of supervision. And eventually Alzheimer's disease is fatal, because the disease will progress in the brain to the major life-sustaining areas of the brain. So it may shorten lifespan, but not necessarily significantly so, especially if it's detected early and treatment begins early. In the brain, Alzheimer's disease is associated with 2 abnormalities, both of which will begin to cause degeneration of the cortex and the hippocampus in the brain. Those 2 abnormalities are known as amyloid plaques and neurofibrillary tangles, or NFTs. Amyloid plaques are usually just referred to as plaques. And these plaques are made up of a protein called amyloid. You see a picture of a plaque on the slide. A plaque is just an abnormal deposit. Amyloid is a protein that is normally produced in the brain, and our brain uses it all the time. But due to some mutation, the amyloid protein chain is cut abnormally. So instead of having 2 pieces of about equal length that go on to do their thing in the brain, an amyloid chain is cut such that there is a very small piece and a very big piece. The big piece is too big to travel through the blood vessels, to go through tissues, to do what it is it needs to do, and it ends up depositing in the brain as a plaque. So when we see the form of amyloid that is too heavy, it's heavier than normal due to some mutation, then we begin to see the plaques accumulate, and that begins to kill the neurons in that area, because they can't get the nutrients that they need, and wastes can't be carried away as they normally would be, because the plaque is an actual roadblock for that local network of neurons. There has been some connection to Alzheimer's disease to a genetic link, so there is a genetic risk for it, but it does not necessarily mean that a person who has the genetic marker for Alzheimer's disease will necessarily develop Alzheimer's disease. More often than not, Alzheimer's disease is not of a genetic origin. It is just the result of some mutation along the way that results in this abnormal splitting of the amyloid protein. The other abnormality that can be detected is tangles, neurofibrillary tangles. These happen within neurons. So plaques happen outside of neurons. Tangles happen within neurons. In tangles, there are filaments within the axon of a neuron. And those filaments are used to carry neurotransmitter molecules up and down the axon, to carry nutrients up and down the axon. It's basically just the little highway system within a neuron. For some reason, those filaments get tangled within the axon, and therefore the neuron can't communicate, it can't receive nutrition, carry away waste, it can't do the things it would normally do. So as a result, that neuron dies. So both abnormalities result in neuron death. And what we're going to begin to see is a shrinkage of brain tissue. The brain becomes less dense and has less volume. If you take a look at the next slide, it is actually a progression of 3. What you see first is a normal picture of a brain where we see the nice cortex, we see what are called plump hippocampi. The 2 hippocampuses are nice and plump, they're full of neurons. And then one area that may also be indicated is the entorhinal cortex. That is at the very base of the cortex in the frontal lobe. And that is one of the first areas that we see plaques appear. So if someone is at risk for Alzheimer's or their cognitive symptoms indicate Alzheimer's disease, that is one of the first areas that an MRI or a PET scan is going to pinpoint. We can very quickly tell if there has been a loss of volume in that particular area of the cortex. As we progress through Alzheimer's, if you click on to the next image, you begin to see shrinkage of the cortex. That dark tan layer begins to shrink in depth because we're starting to lose neurons in the cortex as a result of plaques and tangles. In the middle of the brain is a series of ventricles. Ventricles carry cerebrospinal fluid through the brain. That brain has nutrients, or the ventricles carry nutrients and carry waste in, through, in, and out of the brain. As the brain density begins to get smaller, those ventricles begin to enlarge, and you can again see that on an MRI scan. The hippocampus also begins to shrink. And if you progress to the last image, you will see kind of late stage, or what we would call moderate to severe Alzheimer's progression, where you see extreme shrinkage of the cortex, the ventricles in the brain are severely enlarged, and the hippocampus has become very, very small. Eventually, with continued degeneration of the brain, we will begin to see its effects in life-sustaining areas, and that is when Alzheimer's disease is ultimately fatal. But there is no reason to believe that lifespan is necessarily negatively impacted by Alzheimer's disease if treatment is started early. That is why early detection is so critical. From first diagnosis, a person's projected lifespan could be 20 years, maybe even more, with proper medication. Medication that is given is used to retain the function of neurons that are left while this degeneration is going on. In Alzheimer's disease, the neurons that are affected most are those that use acetylcholine as their neurotransmitter. So most of your first-line drugs for Alzheimer's disease will boost acetylcholine function in the brain. That is, to give an extra boost to neurons that are still functioning so they can take over the work of neurons that are being lost to Alzheimer's disease. So it is possible to slow down the progression with proper diagnosis, medication, and of course cognitive exercises too. Keeping that brain healthy will also prolong a person's lifespan with Alzheimer's disease. That is the end of the lecture on remembering.